Okay, so a lot of times with sequences, you will start to find what are called partial sums. And that is just to simply add together the first however many terms of the sequence we want. So this says that the first partial sum is simply just the first term. The second partial sum is the sum of the first two terms. And whatever the subscript is on the s, that is the first however many of those terms you're supposed to add together, right? So S of n is the sum of the first n terms in general. So find the first four partial sums and the nth partial sum, so we're going to have to write a formula for it, of the sequence given by a sub n equals 1 over 2 to the power n. Okay, well, to find the partial sums, I need the first four terms, right? So if I want the first four partial sums, I'm going to need at least the first four terms. So let's go through and find that first. A sub 1, if I plugged in 1 into that, I would get 1/2. A sub 2, my second term of my sequence would be 1/4. The third term of the sequence would be 1/8. And the fourth term of the sequence would be 1/16. Okay, once I have that, I can go ahead and start finding our partial sums. So the first partial sum is the same as the first term. It's just the sum of the first one terms, so that would just be 1/2. The second partial sum is to take the first two terms, 1/2 and 1/4, and add those together. So 1/2 plus 1/4 would be 3/4. The first three partial sums would be 1/2. The third partial sum would be the sum of the first three terms, 1/2 plus 1/4 plus 1/8. So we basically already know that 1/2 plus 1/4, that's 3/4. We just found that there. So 3/4 plus 1/8 would be 7/8. And the fourth partial sum is 1/2 plus 1/4 plus 1/8 plus 1/16. So that's 7/8, right? All of that would give me 7/8. 7/8 plus 1/16 is going to be 15/16. Okay, so I chose to write out the terms every time because when we go to write the nth partial sum, sometimes the pattern with sums is not as easy to see as it is with just looking at the terms, right? So if I'm looking at the partial sums, sometimes that pattern is difficult to see. But if we write out how we got those terms, a lot of times that will help if it is difficult to see from just our answers what that pattern may be. So I went ahead and wrote those out even though I probably didn't need to do that. For example, like I said, like for the third one, I know it's just what I got for the second one plus the next term, and then it's what I got 7/8 plus the next term, 1/16, and so forth. So there are some shortcuts when it comes to finding those, and you don't have to write all that out. But I would advise you to write all those things out so that if you're trying to find the nth partial sum, it makes it a little bit easier on you. So what patterns do we see, right? That's what I want to look at here. Well, it's a fraction every time, so I'm going to go ahead and write this as a fraction. If you look at the numerator, 1, 3, 7, 15, I'm really not seeing much of a pattern there, and you may say, well, you add 2, then you add 4, then you add 8, and the next time you would add 16, right? So you're probably thinking to yourself, like, I see some kind of pattern there, but can you write that explicitly over here? Like, what are you doing with 3 to get 7 on top, right? Or what are you doing with 4 to get 15, and so forth? So it's a little bit challenging to come up with that. On the bottom, 2, 4, 8, 16. Hey, that's a pattern I know. 2, 4, 8, 16, those are the powers of 2. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, right? The powers of 2. So how do I write the powers of 2? That's 2 to the power n. If I plug in 1, I get 2, and 2, I get 4, and so forth. So I know my denominator is going to give me it's just going to be 2 to the power n. So whatever, if I want to know the 50th, partial sum, I know that my denominator is going to be 2 to the 50th, whatever that number happens to be. Well, once I have that, now what I'm going to look for is the numerator, right? So could you compare, even though we kind of saw a pattern with the numerator, could you compare the numerator with the denominator every time? And I hope that you see that the numerator is simply just one digit less than what the denominator is every time, right? The next one I think you can probably tell is going to be 31 over 32, right? It's just one digit less. So it's going to be whatever I have in the denominator, which is 2 to the n, but then one digit less than that, so minus 1. And that would give me a formula for the nth partial sum. If I want to know the sum of the first 10 terms, I could simply just plug in 10, and it's going to be 2 to the 10th minus 1 over 2 to the 10th. Okay, so that's partial sums. Next we have what's called sigma notation. And sigma notation looks like this. It's sigma, it's a Greek letter, but it looks like this big E, right? And there's some parts here that you're concerned about. The inside here is a formula that we're going to use. So in this first example, it's k squared, right? It's some formula, and then there's a number on bottom. In this case, it says k equals 1, and then there's going to be a number on top. And what you do is you start with plugging in the bottom number, and you end by plugging in the top number, and you plug in every number in between into this formula, and then the big sigma just says add all that together. So notice how we're adding all of those terms together. So once I do an example here, that'll make a lot more sense. So my formula is k squared. I'm starting with k equals 1. I'm ending with 5. And I'm going to add all those things together. So what I'm going to do, plug in 2 squared, plug in 3 squared, plug in 4, plug in 5. And I stop at 5 because that's my number on top here. So I started with 1, I ended with 5, I plugged them all into the formula k squared, and then I'm going to add all of those things together. And if I add all those numbers together, I get 55. Okay, the next one, 1 over j is our formula. We're starting with 3 this time, so I'm going to do 1/3 plus 1/4. Again, I'm stopping at 5, so plus 1/5. 1/3 plus 1/4 plus 1/5. We get a common denominator there, which would be 60, so this would be 20 over 60 plus 15 over 60 plus 12 over 60. 20 plus 15 plus 12 would give us 47 over 60. Okay. If you have a partial sum written out, can you write the sigma notation for that? That's an important skill to have as well. So I think it's easy to see what the formula is here. It's k to the power 3. I'm going to start with k equals 1, and I end with k equals 7. Now, this one is very easy to see because I actually see 1 cubed plus 2 cubed plus 3 cubed. But if it were the answers to those, could we come up with the formula, right? So if it was 1 plus 8 plus 27 plus 64 plus 125 and so forth, would you be able to recognize that, hey, I'm just cubing all of those numbers up to 7? Again, important skill to have there, but that's how you write the sigma notation for that. On number 2, there's a couple ways you can write this. So a lot of people would probably choose to say, all right, we start with 3. So k equals 3. We end with 77. And our formula is just the square root of k. I'm going to challenge you a little bit to do this a little bit differently, because a lot of times it's advantageous to start with 1 on the bottom. So if I started with 1, what would my formula be, and what would be the number that I end with? So if I start with 1, how do I get that to be a 3? Well, I would just do k plus 2 inside there, right? 1 plus 2 is 3, 2 plus 2 is 4, and so forth. So I could make my formula k plus the square root of k plus 2. Then I can start with k equals 1, then what do I end with? I would end with 75. Here's why. Here's why I would choose to do this. A lot of times you're going to want to know how many terms there are in this partial sum. Like, how many terms did I add together? It's very easy to see if you start with 1. If I start with 1 and then with 75, I know there's 75 terms. I would caution you a little bit because you might look at this and you might say that there are 74 terms there, right? So be careful. There are 75 terms there. If I go from 3 to 77 and I count both 3 and 77, I get 75 terms there. If you start with 1, that's one advantage of starting with 1 is that the top number is how many terms there are, which is going to be an important thing for you to know. But you don't necessarily have to start with 1. It just if it's easy to rewrite your formula so that you can start with 1, I would recommend doing